The purpose of this video is to discuss the question of how the triangular neighborhood networks can be scaled. This is one triangular neighborhood, and what we can do is introduce another set of nodes between each node. Now in the adjacent neighborhoods like this and like this and like this, the effect applied systematically to every neighborhood is that we now have a series of 6-edged nodes that fill the intervening space. So this is one of the ways in which scaling of triangular neighborhood networks can be accomplished. This process of scaling is really very important, because if we want to go, as we did in the earlier video, from very small networks to much larger networks, we have to be able to produce numbers of nodes and numbers of edges that are exceedingly large. And so this discussion about scaling can do that. A triangle neighborhood can be represented in this case by 3 5-edged nodes where there's one triangular neighborhood that they share together. The scaling of this triangular neighborhood can be accomplished by adding one node between the 5-edged nodes. In this case, there are 3 6-edged nodes in orange that are introduced into the structure. The same the feature of this scaling is that there's a triangular neighborhood here that's introduced. We can add 2 nodes between each of the 5-edged nodes here and here, and the central feature of this scaling is a 6-edged node in the center. The same sort of thing can be applied by introducing 3 nodes between the 5-edged nodes, and in which case the central feature is a triangle here, this triangular neighborhood. Of course, we can introduce as many nodes as we want between the given nodes, and of course, once you apply this to any given triangular neighborhood, then it is also applied systematically over the whole structure. In addition, there are other ways that we can do scaling. Instead of having the 5-edged nodes point to each other, the 5-edged nodes, or the triangle that we're concerned with, can be organized such that the edges of the 5-edged node point towards each other, in which case a single 6-edged node is introduced into the structure. So this is the point-centered scaling as opposed to the edge-centered scaling. So here we introduce an extra node here between the 5-edged node and the central node, and now we get these 3, as before, 5-edged node edges pointing towards the center, just as we did here and here and here. So this is the scaling 2 in the point-centered viewpoint. And then this is the scaling 3, I guess I should show them side by side, where there are now 2 nodes between the 5-edged node and the central node. Again, the edges point towards each other. So this is the point-centered scaling of a neighborhood. But there's yet another way of doing this, and that is to have the 5-edged nodes not the edges of the 5-edge nodes not point to each other. So instead of pointing towards each other, they did in the one case, or pointing towards the center as they did in the second case, here they point askew to each other. So these two are skew, these two are skew, and these two are skew. And so the result is a triangular neighborhood here in the center of this thing. And so this is the skew scaling, and it can be applied here, where once again there are now two nodes in the scaling, and the central feature is a triangle here. This can also be done so that these edges, these nodes, go further and further away. This can be applied systematically to the whole structure, but of course you have to have the initial conditions correct. And I've experimented with that in some way, and it works out, but I'll limit myself in this case to this particular scaling. The triangular neighborhood networks can be structured so that there are only 6-edge nodes. The 6-edge node in the center of this particular sample is in orange, showing that there are 6 edges coming into each node. The virtue of this sort of construct is that it can be as large as you wish. It can go on, one could say, to infinity, but really just to a very large extent. The other property of I call this the ground state, okay? And so one of the properties of the ground state is that it can be formed into pipes and still be a triangular neighborhood structure. The pipes, of course, can be banded pipes. I'll show you those in a second or two. Or they can be the vertical pipes, as you see here, and the pipes can have twists in them. So I'll show you the various examples. For example, here is a vertical pipe that has a circumference of 4 nodes. So there's 1, 2, 3, 4. And this pipe is as small as the vertical pipes come. The property, it seems, of the vertical pipes are that they can only be in circumferences of 2. So this is 4 and this is 6. You can see the difference in the circumference of these two pipes. The vertical pipes are one construction. In addition to the vertical pipes that we just looked at, we can construct banded pipes. A banded pipe has a circumference of, in this case, 3 edges. So this is a 3 circumference banded pipe. You can see that rather well. In contrast to the vertical pipes, in which have to be displaced from each other by 2 units, that is 4, 6, 8, and so forth. The banded pipes can be of integer differences. So this is a 3 pipe, here's a 4 pipe. You can see the difference in the circumference here. We could make a 5, but here's a 6 banded pipe. And so this is, you can see the differences in the diameter and circumference. In addition to the banded pipe, there are spiral pipes, pitched pipes. So this is a pipe which has a pitch of 1. It happens to be left-handed, and it's a circumference of 5. In contrast to that, we have here a right-handed pitched pipe with a circumference of 6. And then we can have additional pitches. Here's a 7 pitch, a 7 circumference pipe with a pitch of 2. And you can see the structure like this. So we showed before how there are vertical pipes and banded pipes. And so at some point I asked myself the question, could you convert a banded pipe into a vertical pipe or vice versa? And the answer turns out to be yes. It's rather amazing. So this is a structure which combines the banded pipe here in blue and the vertical pipe here in green. And you see that there are, in purple, there are 6 edges that act as the interface between the banded pipe and the vertical pipe. And that these are 7 edge nodes, and then there are 5, and then 7 and 5 around the circumference of the structure. The trouble with this is that it's sort of tight, and you see this element here is sort of bent because the 7 edge node here and the 5 edge node and the 7 edge node there's too much curvature in this area. And so although this is syntactically correct as far as the triangular neighborhoods are concerned, whenever one sees this sort of bending in the structure, it's an indication that the structure is not happy. So I looked a bit further, bigger structure, and this is what I found. That is, if we add more purple edges to the interface between the banded structure and the vertical structure, well, then we have a much happier structure. Here there are 3 sets of looks like 5 edges, and now we have 7 edge nodes here and here, and 5 edge nodes in various other places, and even 6 edge nodes. So this is a nicer structure, and yet you see how much purple there is as the interface between the 2 structures. So then I went a bit further even and added some more purple to the structure, and here's the banded pipe on the bottom in light blue, and the vertical pipe in green, and then there's quite a bit more purple structure here between the 2, and then it turns out that there's even a bigger structure like this that acts as the interface between the banded pipe and the vertical pipe. So in all, there are 4 structures. Let's see if I can fit these into the camera. Let's see whether the camera just about sees that, yeah. So there are 4 structures going from unhappy and small to okay to larger to largest, or not largest, but larger. And each of these structures has the effect of converting of banded pipe into a vertical pipe. And that's rather interesting. And so I played with each of these structures in turn, but particularly with this structure here. And by means of edge rotation, where the 5 and 7 edge nodes would be changed by rotating, for example, that edge, when you rotate this edge, the bandedness moves that way, and then when you rotate this edge here, the banding moves this way, and the structure becomes more vertical pipe. And so depending on which edge is rotated, of course you have to rotate all of them around the structure, the type of structure will move either to become more vertical or more banded. And that's really rather interesting. Now, how in these larger structures, I didn't investigate that, but again, edge rotation should move systematically around the structure should move the interface between the banded and the vertical, either in the banded direction or in the vertical direction. And so I'd have to do that, show that. I don't think I've done that. But this is very interesting. And because we'll see later on that these structures play different roles in different configurations of structure, and being able to convert one into the other in principle is very interesting. One of the virtues of the triangular neighborhood networks is that you can, the ground state is that you can concatenate any structure, any pair of structures by means of triangular neighborhoods. So I've colored this ground state here so that a particular triangular neighborhood is highlighted in orange. But I also have an icosahedron, which is just a small ball-like object. These ball-like objects are called torus 0 because they have no toroidal holes. But in this case, I've colored the portion of the icosahedron again with orange edges. And so what we can do is we can take this structure and concatenate them together. So if I color the nodes that are affected by the interface both here and here, what we wind up with is the following structure. So here we have the ground state with the icosahedron attached to it. Now I've changed the connecting elements from orange to purple, but each of these, there are 3 nodes, each with 9 edges. 6 of the edges are supplied by the ground state, and 3 of the edges are supplied by the icosahedron, so that there's a threefold symmetry here in the attachment of the icosahedron to the ground state. We needn't have a ground state, and we needn't have an icosahedron. They could be any 2 objects, and the triangular interface on either one, on both of them, can be used to concatenate the structures together. This is a constructive method, and but this would not be used in natural evolving systems. The concatenated structure can also be interfaced with a 3-pipe. So here we have a situation where we have the ground state, where the purple shows how the ground state is interfacing to the 3 circumference pipe, and then the 3 circumference pipe is interfacing, in this case, to an icosahedron. And these are all in purple. So in contrast to the case where the icosahedron was directly connected to the ground state, in that case there were 9 edge nodes. Here there are 8 edge nodes. And then where the 3 circumference banded pipe connects to the icosahedron, these are 7 edge nodes. And so this has a total curvature of 9. So this is, of course, any 2 structures, doesn't matter, can be connected by means of a triangular interface to each other, and we can use a pipe, a 3-pipe in this case, to connect the 2 structures if we wish. This is an icosahedron TNN. Here the red shows the one triangular neighborhood, 3 edges, and each node has 5 edges coming into it. This is the most primitive structure. Here we see the first scaling of the structure. Now there's one node between each of the 5 edge nodes shown in red, and so the central feature of this structure is a triangle, the neighborhood here. This is the next scaling in which there are 3 nodes, so each of this was the original node put into place between the 5 edge nodes, and now between this edge another node has been placed, and the same with between this edge. So this rather nicely shows how the triangle neighborhoods syntax enables the scaling of a structure. And then the next structure here, I didn't put the red triangles in, but you see now there are 5 nodes and 7 nodes in between. And then finally, this is a much larger structure. So the scaling has the effect of increasing the size without changing the shape. Later on, I will use this structure, I think, to show how the surface can be deformed by edge rotation and defect propagation. This is an example of pipe. This has a 20 node circumference and a length of 10. So this again shows that pipes can be constructed. This is a much larger pipe which has a circumference of 10 and a length of 100. I can back off from this like this. Actually, it looks more like 50. But this is a banded pipe. You can see how the banding goes around the structure completely. And this is an example of a small icosahedron with one nodes put in between each of the 5 edge nodes. So it's a scale 1 bowl and then a 6 diameter circumference pipe. The curved nodes, the 5 node edge nodes here, are in purple, and then as the bowl interfaces with the pipe, there are 7 edge nodes here, and then these are just artifacts at the end of the structure. This is a very large pipe. I guess this is 100, and this is the junction between the 2 pipes. And finally we have 2 bowls put together by a pipe, a 6 circumference pipe. So again, these are all beautiful structures. The coloring, the purple shows rather nicely where the curved nodes are, and this viewer that I'm using is King, which comes from the Richardson lab at the Duke University School of Medicine. I've been using this for many years, and it's really very effective. The programs that generate these structures are written in Fortran and run on my laptop here. So it's relatively easy to build these structures. I mean, it takes I think a thing like this would take a day or so to do. The same with any of the others. Once you learn how to make pipes, well, then the program will construct a pipe of any diameter or length. So these are all very primitive objects, and eventually I'll show you some other a bit more complex, but the graphics work quite nicely.